Hi, 詹景祥。So how are you guys doing with PA6? It can be a little bit tricky, I have to say. You do want to be careful. Using differs. Okay, it's time. Let's go ahead and start. Today, we only have one thing to really enforce. What's doing this week? Quiz 18, 19, and 20. Hopefully, we get to quiz 20 today. PA6 is also doing. Okay. So I see more teams struggling with PA6. Okay. So the key is where you use defer and where you close, okay, those connections. Okay, sorry, I just accidentally touched my mic. I hope it's not bursting, okay, to you guys that are remote. Good, so let's go ahead and move on to the lecture. So I don't know about you. I am actually pretty excited today because we'll finally talk about TCP's reliable data transfer mechanism. All right. Good. So first thing we need to talk about is the timeout interval, which we covered already very briefly on Tuesday. Okay, so what we know clearly is this. We don't like to set it too short because premature timeout, unnecessary retransmission might happen. We don't want to set it too long because then we'll be slow retransmitting packets. The idea is to set it definitely longer than the round trip time. Now, the tricky part is this. The round trip time actually vary quite a bit over time, right? So even though we know how to calculate a round trip time to measure one round trip time at a particular point in time, so that is called the sample RTT, all we need to do is to subtract the time between the data being sent and the corresponding ACK coming back, right? So that way we get a sample RTT. Well, be careful though. Sometimes we might be retransmitting data. So in case there's a packet that we need to retransmit, we better ignore that particular sample RTT. So this is so that we do not accidentally including a too long RTT, okay, or too short RTT. So because it can be a bit confusing. Should I be subtracting the ACK receiving time from the first transmission or the second attempt? Okay. So we ignore the retransmission's sample RTT. We take one transmission's sample RTT. But then sample RTT varies, so we don't want to use the instantaneous sample RTT. Okay, we want to somehow smooth the RTT, calculate some sort of average. Okay, some sort of average. So this is what this is doing. Okay, so that smoothed sample RTT is now called the estimated RTT. And so this line can be read more like a code in a C program or Python program, or now Golang program. So the way it works is this. Once we get a sample RTT, okay, we'll take a weighted average, so weighted by alpha, to the previous estimated RTT. So at any given point in time, there's a smooth average of the sample RTT. and there's a fresh, new sample RTT, and we take a weighted average of these two. And that is going to be the new value for the smoothed average RTT, the estimated RTT. Okay? So we use the existing estimated RTT and take an average of that with the current sample RTT. Okay, that will be used as the next estimated RTT. So in case we get the next sample RTT, we then use that value here, okay, and take the another smoothed average. So it's not like the usual average we're using, right? Calculating, for example, the average of the midterm exam score. So it's a weird kind of average, okay? And the official term for this kind of average is this: exponential weighted moving average. Okay? You can probably sense why it's called moving, right? Because it's retaking the previous estimate and then use it for the next one. Okay? And the new one will be the previous for the next round, okay, and so on and so forth. So it's iterative. Okay, that's why it's called moving average. And because we are using an alpha, a parameter, okay, and this alpha can only be in between 0 and 1, so it's not a uniform average, it's a weighted average. The reason that we call it exponential moving average is because of this. So every time we are taking a 1 minus alpha portion of estimated RTT. So you can imagine, so let's assume we now have a sample RTT. This sample RTT, currently we multiply it by alpha. The whole thing is going to become the estimated RTT for the next round. In the next round, the whole thing here will be multiplied by what? Another 1 minus alpha. So this sample round trip time will be multiplied by 1 minus alpha. And yet the next interval, next iteration, there'll be another 1 minus alpha. So over iterations, sample RTT will be multiplied by n numbers of 1 minus alpha. Okay, the more iterations, the bigger the n. So essentially, the influence of this sample will decrease exponentially over time. So we know that exponentially multiplying a factor that's less than 1, that means that, okay, that value's influence to the smooth average will be really, really fast dropping. Okay? So that is why this thing is called the EWMA. Okay, EWMA, exponential weighted moving average. A typical alpha for TCP's round trip time estimation is 0.125, which means the variation is usually very large. So let's not take too much weight on the instantaneous sample. So how do you like this average versus the regular average we use? What do you think? Do you like this better or the regular average? Well, think about how many variables, how many data entries you need to store in the TCP sender. Right? TCP sender needs to estimate the retransmission timeout interval. So this is something that the sender part needs to do continuously. So if we do it this way, how many variables we need? Not just one, right? We just keep this because the next sample RTT is going to be part of this. So what's really nice about doing this type of moving average is because memory requirement very low. If we need to store all the history of these sample RTTs, right? The longer the sender runs, the more memory we need to store all the previous RTTs. Okay. Of course, you can think of another way to implement the regular average, right? You could store the average and the number of times that we have samples. Okay, that would also reduce the memory requirement. Okay, but that's still two variables. In this case, just one. Okay, and what's another thing that's nice about this is that the individual sample gets weighted down exponentially fast. So for things happening on the internet, there's short range dependency, all right? But longer term, usually the events are more irrelevant. Okay. So that EWMA, you might see actually happening again and again and again, okay? Estimating things that's continuously running. So this is to illustrate the instantaneous RTT, the simple RTT, okay, will be the blue one. You see lots of fluctuations. Okay. The estimated RTT, which is the smooth average one, then you see, flatter, more steady. But now let me ask, are you going to just use the estimated RTT as the timeout interval? Okay, I see some of you shaking the heads. I guess many of you behind are also thinking the same, right? Why? Hey, wait, if we use the pink line here as the threshold, so all these instances where the sample RTTs is higher, we get to retransmit, right? Wow, that's quite a few of these. Not good. That's why the timeout interval is not quite just getting the estimated RTT. It's estimated RTT plus a safety margin. And hopefully the safety margin is large enough so that there are only very, very, very few instantaneous RTTs that's going to exceed, okay, the final timeout interval. Okay. So the way to go on is to try to find out what should be the safety margin. So what that safety margin meant is that we somehow need to capture the variation, the degree of variation, and include that in the timeout interval. So let's try to estimate the variation of the round trip time. What is that? Well, when we are learning basic statistics, right? Previous slide, we were just calculating the average. When we teach calculating average of a set of numbers, what else do we teach? Calculating the standard deviation. Standard deviation is essentially to quantify the variation, the deviation, okay? But it's the very standard one, so it's called the standard deviation. Here you see how TCP sender estimates the deviation. It's definitely not the standard deviation. It actually looks like this. So you first define a variable, DEV RTT. So this is the standard, this is the deviation of RTT that TCP is estimating. The way it works, hey, look at this. One more time, right? The previous deviation RTT plus the current deviation, the instantaneous deviation. What is that? The current sample subtracting the average. So the difference of the current sample to the average. That's the deviation. And we do weighted sum, and this time we use alpha, beta, and 1 minus beta as the weight. So this is once again, exponential weighted moving average. So the standard so the deviation we're calculating is not just instantaneous deviation. It's also a smoothed, okay, average deviation, and it's not like the standard deviation. So eventually, what we do is adding to the average with 4 times the deviation. Why 4? If you recall normal distribution, right? If we add 4 times the standard deviation to the average, it should cover what? 99% and maybe more, okay, of the samples. So you see here, the timeout interval here is set to the average plus 4 times deviation. Okay, so this is also, hopefully, there's only less than 1% of the RTT sample being higher than the timeout interval. So very few retransmissions should supposedly occur. So that was estimating the timeout interval. Did we do any of this in go back in or selective repeat or RDT 3.0? No. So obviously, in TCP, something that we really need to implement, the timeout interval needs to be clearly defined. So this is the first difference. Okay, first thing that's unique in TCP's RDT to the previous RDTs we've studied. Now let's move on, okay, and see what else are different or what else are similar. So first, let's look at the stuff that are similar. Okay, so TCP does pipelined RDT, and the acts are cumulative. And there's only one retransmission timer. And it retransmits when the timer times out. So based on these features, do you find this one being more go back in or selective repeat? Well, obviously, more go back in, right? But you see, another thing being different is that TCP actually also retransmit, okay, upon receiving duplicate acts. But the way it's doing that is a little bit tricky. Okay, we'll talk about it maybe next week, okay, or at the end of today. So let's assume a very simplified TCP sender, okay, where we kind of ignore this extra mechanism trying to retransmit upon receiving a certain number of duplicate acts. So let's ignore that for now to keep it simple. And let's ignore that TCP, in addition to doing the reliable data transfer, also do flow control, congestion control, which means they might actually adjust the window size. Okay, so the window size, unlike in go back and selective repeat or RDT, they're all fixed. In TCP, that window size could vary. So let's ignore these two additional differences for now, so that the finite state machine will look straightforward. Okay. So the first feature is nice. The finite state machine is at least simple. There's only one state, 3 transitions. Okay. To begin with, there's the initialization process. So previously, when we were talking about the finite state machines, I kind of just neglect this part. Okay, so there's an initialization phase. The necessary variables will need to be initialized. Okay, so there's an initial sequence number and send base as well as the next seek num will all be set to that value. Okay, so send base and next seek num are the same. So you see that this is the beginning of a flight. First transition is getting a call from above, so having some data to send. Okay, this is very common. We see that in go back in selective repeat, in RDTs, 3.0, et cetera, et cetera. But this time, in TCP's finite state machine, the description here, I try to be a little bit, talking in English instead of more like pseudocode. So please excuse me for being a bit fuzzy here. But essentially what's doing is very similar. First of all, create a segment. All right. And that segment sequence number should be the next seek num, right? Because next seek num is the variable, okay, tracking. What is the next byte that is allowed to be sent? And then the next thing is what? Yeah, called UDT send to begin sending that new segment, okay, through the network layer and down. In go back and then you recall this, right? If the timer is not currently running, start timer. For the first packet, definitely. Okay, the condition will be true, and therefore we start timer. And for every RDT, you see, okay, the next seek num needs to be incremented. But this time in TCP, we are counting segments by the bytes. So the next seek num should be the size of the data. So number of bytes of the data that we need to send. So are you comfortable here? Most of you heard me saying that I'm trying to be a bit fuzzy here, then you are okay with it. But here, something that I actually omitted is this. Before we are allowed to send, we need to check whether the next seek num is within send base plus the window size, isn't it? Okay, good, very good. So to be precise, this transition should still have that condition check. All right. Very good. Now this transition is clear. Now let's look at the second transition, which is the transition we receive an ACK from the underlying channel. So an ACK received, and we extract the sequence number out of the ACK packet. Let's set it to Y. So the next thing we do here is check whether this Y is bigger than send base. If it is, what does that mean? So this is an ACK for one of the packets, okay, that are still in flight. So sender is still having that packet in yellow, isn't it? So if Y is bigger than send base, we call this also a new ACK. It's an ACK we have not yet seen before. The sender has not yet seen before. If that's the case, great. It's a new ACK. Let's set the send base to Y, because Y is indicating that all the sequence number data before that are acknowledged, because ACK in TCP is cumulative. Okay, and then we check if there are still not yet ACKed segment, okay, in the sender's window. Okay, then we restart. If there, okay, yeah. So if there are still some packets waiting to be ACKed, we need to start timer, right? Because these packets can be lost, so we definitely need to keep a timer for them. Otherwise, if there are no packet waiting to be acknowledged, then we don't need a timer anymore. Stop it. This, you want to be a little bit careful. Although TCP is very much like go backend, but in go backend sender, when we are receiving acknowledgements, the way we handle the acknowledgements are a little bit different. If I go back a few slides, you'll see in go backend, state machine, right here. This is go backend state machine. So that transition we just went through is very similar to this. Is very similar. Is very similar to this transition at the bottom, isn't it? We are also receiving an ACK. So let me make sure that you can see the details a little bit more clear. There we go. So this is the transition that's actually equivalent of the one that we just went through, right? We receive an acknowledgement. It's not corrupted. What go backend does is to go ahead and just extract the sequence number out of the packet, out of the ACK. And then what? Set it to the base, right? So base is actually changed to this value. But the thing is that this can be a duplicate ACK. Okay? but it's okay, right? If it's a duplicate act, base is not changed, so okay, no loss. But we do check this. If the base equals next sequence number, what that means is that there are no not yet acknowledged packets. So we stop timer for sure. But everything else, if it's a partial acknowledgement, it's a new packet or a duplicate packet, either case, we do what? Restart timer. So in go back in, we kind of restart timer very frequently, even for duplicate packet. But in TCP, what you just saw there is there's a if condition there. Restricting such that we will only refresh timer when it's a new act, but it's acting partially of the packets in flight. Okay, if it's a duplicate act, we actually kind of ignore it. Okay, so what's different is here. We do check if the Y is greater than same base, checking whether it's a new one or just a duplicate. If it's a duplicate, what do? Well, there's nothing here. Duplicate X, ignored. So this is the second difference, of TCP to go back in. Last one, this one actually looks very familiar. This is just the timeout event. And all we do there is retransmit the not yet acknowledged segment and then restart timer. Straightforward. So from the finite state machine here, you see there's a major difference again here. All right? Okay, so this next slide, what I'm showing is, hey, it's actually identical to the finite state machine I actually illustrated. The left here is the first transition. Upper right is the transition on the right. Okay, and the last one here, ACK receive, is the transition at the bottom. So these data received from app, receiving ACK, and timeout are the three transitions in the finite state machine. And this is kind of like, talking about TCP sender's mechanism in three kinds of events. Okay, that can be triggering TCP sender to do different actions. Now, with that said, it might not be that hard to imagine. You can actually write a pseudocode of TCP sender, right? Initializing the next seek num and initializing the same base at the top, right? For a program, oftentimes initialize a bunch of variables. In the program, now it should be very familiar to you guys. In a server program, in a server process, oftentimes you start the process running in loops. So sender here is running also in infinite loop. And it's waiting for an event to happen, switch an event. Now in the case of this event, do these. In the case of the second event, do these. Third, and these. So this is getting a call from above. This is receiving ACK, and this is timer timeout. So the finite state machine there, one can actually simplify it to a graph that is only one state, multiple transitions. In that case, you ended up with a pseudocode like this. Right? So finite state machine there, although it's a little bit weird as a way of describing a mechanism, but it actually makes a lot of sense as well. And one can actually transform from finite state machine to pseudocode. Okay, so a lot of times network engineers do this. We do the design using the finite state machines. Okay, and later on, we try to transform from finite state machines to pseudocode so that the programmers can work on the implementation. Then we just go through three examples of TCP's round trip RDT mechanism. first one, very straightforward. Host A there sends a packet, sequence number 92, okay, and we're sending certain number of bytes of data. B here generates an ACK, okay, from quiz 19, you know, right? What is the ACK sequence number there? 92 plus the number of bytes. In this scenario, we lost the ACK packet. So TCP sender here will go into timeout and therefore retransmit from send base. Okay, and this time we get acknowledgement sequence number 100. Very simple case. And then the two cases, slightly complicated. The one on the left actually demonstrates the benefit of doing cumulative ACK. Look at that. Host A sends 2 packets back to back. Okay, sequence number 2, sequence number 100. Host B, upon receiving the first packet, sends back ACK 100. Upon receiving the second packet, sends back ACK. Well, this time 100 plus 20 bytes, 120 in the sequence number. Well, the first ACK might get lost, but since this is cumulative ACK, when sender receives the second ACK, hey, both of the data packets are acknowledged. Okay, so it's not necessary that all the ACKs arrive at the receiver. As long as the later ones arrive, then we're okay. And therefore, after receiving ACK 120, sender sends the next packet, starting with sequence number 120. The scenario on the right is demonstrating, well, in case we set the timeout interval too short, then we have premature timeout. So these 2 data goes to the receiver. Receiver did send ACKs, but timeout event occurred earlier before the sender received the ACKs. So retransmission of sequence number 92 happens here. Now these ACKs, after being received by the sender will acknowledge, okay, both of them are good. Okay. If there are more data, they'll be generated here. Now this guy is going to trigger an ACK coming back. That's going to come back, but host A is not going to do anything. All right. But some of you were like, wait a minute. When the timeout happens here, hey, don't we retransmit from the same base all the way, right, to all the outstanding packets? This is supposed to go back in. So we should be resending packet sequence number 92, as well as sequence number what? 100. What's going on here? Yeah, that's yet another difference, okay, between go backend and TCP senders, RTT. It's here, right here, timeout. The way timeout is being handled, slightly different. And it's because in TCP, there's something called condition control. So what the condition control in TCP says is, whenever there's a timeout event, we need to reset the window size down, all the way down to just 1 packet. 1 maximum segment size, okay, only these many bytes. Retransmit only 1 packet that's not yet acknowledged. In the meantime, set the timeout interval to twice as high. So you can imagine, if this retransmission here is lost again, timeout will happen again. Window size will still be 1, we'll be still retransmitting that first packet, but the timeout interval will become what? 4 times the original value. So TCP's condition control there is quite conservative. Okay? If timeout event occurs again and again and again, the wait, okay, to timeout will grow exponentially faster, exponentially longer. So finally, you see timer setting here. So in fact, in these two other transitions, timeout intervals are also set, initialized. The reason that we need to set those is because, hey, there's a start timer here. Okay, if this is the beginning of the flight, the timer needs to be reset. Otherwise, we could be using some very long timeout interval in case there's a timeout event earlier. Similarly here, right, we're restarting timer. So definitely we need to set the timeout interval appropriately, which is just the simple RTT's average plus the average deviation. Good. Now we can summarize. RTT of TCP versus go back N. Similarity, pipeline segments, cumulative ACK, single retransmission timer, retransmission on timeout, no problem. Okay. But unique in TCP, we've already talked about it, right? The timeout interval, how we calculate it, it's well defined. And slightly earlier, right, when we were still talking about the finite state machine of TCP, that transition for receiving an ACK, only the new ACK restart timer. Unlike in go back N, duplicate ACKs also start, okay, restart timer. Now you hear, just now you hear, when there's a timeout, we retransmit only one segment. And the timeout interval gets doubled. But you know what? That's not the only differences. There are two more. And these two more are actually more by design. Okay? Not because, well, hey, you have to implement, therefore we need to define it clearly. Okay? And it's not like this one here, which is a little bit minor. So this is so that we don't refresh timer for duplicate ACK. Therefore, we don't have to wait too long, okay, to time out. Now, these two are actually more elaborated design. So let's start from this, delay ACK. So what delay ACK concerns is the receiver side of TCP. Well, wait, receiver. Until now, we haven't really talked about the receiver of TCP. We talked about receiver of go back N briefly. Do you recall? Maybe we should go back. Just like we went back to the go back N sender. Yeah, it's right here. This is go back N's receiver. So all these differences we talked about TCP's RDT to go back N are only on the sender side. So one can actually try to assume, right, the TCP receiver is going to be also very similar to go back N's receiver. Now let's refresh go back N's receiver. What do we have here? Well, of course, we have the initialization, which is trivial. There are only two transitions. The key transition is here. If we receive a data, the data packet is not corrupted, and the sequence number is as expected, then we extract data, pass it up to the application layer, sends back an acknowledgement packet, and increment the expected sequence number. Straightforward. So if we receive a duplicate data packet, out of sequence packets, all we do is just this. Resend a duplicate packet. There's no receiver buffering, right? We do not really accept out-of-order packets. Now, in that case, we just simply send a duplicate ACK back. Good. With that refresh, let's come back to TCP's receiver, where we have additional mechanisms added to it, the delay ACK. It should be a little bit easier for you to associate. The delay act, this extra mechanism, is added only on the transition we are receiving an expected packet. Oopsie. Okay, so let's focus on these 4 additional conditions. Okay, and I'll show you the receiver finite state machine a little bit. Let's look at the first one. Arrival of in-order segment with expected sequence number. Cool, cool. The second event, arrival of in-order segment with the expected sequence number. Wait. Don't we just have it here? Yeah, if we look at these two as a set, you'll see the differences are these. The first one says, if all the data up to the expected sequence numbers are already ACKed, then we delay the ACK for this new packet coming in. We wait for 500 milliseconds. Only within these 500 milliseconds, there are no more data coming in, then we send acknowledgement. If there's none next segment coming in, then send acknowledgement. So delayed ACK. Therefore, right, so we could have this condition already receiving the first data packet. But the second data comes in immediately. So which is this, arrival of in-order segment with the right sequence number. But there's already a ACK pending right here. In that case, what do? We immediately send a single cumulative acknowledgement back to the sender. So this is a really nice use of the cumulative ACK. As a result, we only send about half of the acknowledgements as opposed to what go back and receiver is doing. All right, so you can imagine receiver finite state machine gets complicated. Now let's come down here. There are 2 more conditions, 2 more events. This is concerning gap. Let's look at the first one. If there's out of order segment arriving, oopsie. In go back and what do? We kind of just discard it, right? And send duplicate ACK. But no, in TCP receiver, we just simply say gap detected. We kind of buffer the out of order packet. Okay. We send back immediately a duplicate ACK, indicating the sequence number of the next expected byte. So the difference is just that we still send ACK, but we buffer the packet. Therefore, creating a gap. So the gap means there's a missing packet in between the packets received in order to the packet received out of order. Well, then this sounds a little bit more like selective repeat, isn't it? It is. On the receiver side, TCP is a little bit more like a hybrid between go backend and selective repeats. Last condition, in case we receive a segment that partially or completely fills a gap, we send a cumulative acknowledgement, acknowledge all the way to all the packets received in sequence. Okay. So if it's partial, then it's only up to the head of the partial gap. Okay. If it's complete, of course, it can move on, and potentially more packets can be acknowledged. So the receiver's finite state machine is actually in the quiz. And it's right here. Okay. Can I bring it up? There we go. Yeah, it's right here. How to read the finite state machine. Let's now focus on T1. T1 is the what? Receiving a packet and the data packet is not corrupted, has the expected sequence number, but it's not filling a gap, meaning it's not one of those conditions at the bottom. Okay. And look at this. Okay, there's no data packets pending. Okay, there's no X pending. What do we do? So what is this condition? Oh, that is the first event, isn't it? Receiving packet in order, no packet pending. So what do? We delay the ACK. So of course we need to extract the data, but eventually here, before sending the acknowledgement, we wait for 500 milliseconds. And we set the status to pending. Pending equal true. What is the other one? The second event is actually in T2. Packet arrived, not corrupted, has the expected sequence, so it's arriving in order. Definitely not filling the gap. But we see that there's a ACK pending. Therefore, what do? Of course, extract data, generate the ACK that is cumulative, and send the ACK. And the rest is the same, except that we change the pending state back to false. What is T4? Receive data, not corrupted, has a certain sequence number. Oh wait, it fills the gap. So what is this one? Yeah, it's the bottom event, right? Bottom condition. What do we do there? We'll have to generate the ACK. Okay, and the ACK is all the way to the last packet receiving order and send it back. Okay, and of course, reset the pending to false. So event number 3 there in delay ACK table is up here. Because that is the condition we send duplicate ACK. So duplicate ACK is sent here. So Q1 is, which transition is delaying X? Which one? T1, very good. Which transition send the new X? Those who say T2, raise your hand. Very good. T2 sends a new ACK, isn't it? Is that the only transition sending a new ACK? Very good. T4 also sends a new ACK. T1 doesn't send any ACK. So I'm missing a, yeah. So I'm not really missing, because in case there's a timeout event, that is going to be default, and we'll send the ACK packet that we have already generated here. So it will still work. Okay. But T1 itself is not sending an ACK immediately. Okay, so T2, T4 do. Q3, which transition send duplicate ACKs? Obviously, T3. Good. Yeah, so TCP receiver, finite state machine, a little bit complicated, but now we went through it. You get the bigger picture. And this complication is because we want to be able to save some bandwidth. Instead of sending individual ACKs for every data packet, we send one after 2 packets. Once after 2 packets. And this is also to take advantage of the cumulative ACKs, you see. Great, so that's all for today. The second improvement, fast retransmission, we'll talk about next Tuesday. All right. So guys over the internet, that's all for today. Feel free to leave. Great. Type things up, definitely. Okay, I see Shu Yu, Yuzhe, and Kevin. You guys are there online. Great. So I'm going to end the stream, guys. All right, so type up your solution for quiz 20, which should be very straightforward today, okay, on Slack.